Then we'll just get started. Looks like that's going. Okay, so since it's been a little bit, let's recap from the top, make sure we understand all the important terminology. So first off, we need to remind ourselves, what is a topology? So a topology on some set X, we're going to call it tau. A topology on X is a collection of subsets of X such that three conditions are met. First off, the set X and the empty set have to be in tau, right? Second, any finite number of elements in tau, take any finite number of elements in tau, or a finite subset of tau, however you want to think about it, finitely many elements in tau, or a finite subset of tau, and the intersection of all those elements has to also be in tau, right? And then finally, take any arbitrary subset of tau, or any arbitrary collection of elements in tau, however you want to think about it, could be infinite, could be finite, then the union of all those elements has to also be in tau, right? And then if we remember, what's an open set?
It's just a set in tau.
It's just an element of tau.
Right.
Yeah, they'll always be sets, but yeah, so an open set is just an element of tau. So re-saying this using open sets, here's how we say it. Tau is a topology on X if three conditions are met. X is open and the empty set is open. Any intersection of finitely many open sets is open. And any arbitrary union of open sets is open. Make sense? Anything weird? Good recap on topology? Feel like we got a grasp for this lecture going forward? Okay, so that was going clear back to section 1.1. Now we're halfway through section 1.2. Section 1.2 was all about a basis for a topology on a set. So let's recap what a basis was. So some basis beta for some set X. A basis beta for some set X is a collection of subsets of X satisfying two conditions. The first condition is that for every element in X, every little x and big X, there must exist some basis element such that X is in that basis element. Every element in X has to be in some basis element. Oh, sorry, we didn't say what basis element was. Beta is a collection of subsets of X. The members of beta we call basis elements. And I'll always use B's for my basis elements and beta for my collection of basis elements. Good with that? Anything confusing there?
Like lowercase b's are your elements?
B
Okay.
will be my element of beta.
Okay.
B will be my basis element. Remember, my basis elements are sets. Beta is a collection of subsets of X. And I'm going to use B to refer to those individual sets and call them basis elements, the elements in my basis. Good with that? Okay, so beta, some collection of subsets of X, is called a basis on X if two conditions are satisfied. For every little x and big X, there exists some basis element, some member of beta, such that X is in that basis element, that member of beta. Follow that? And next, if X is in the intersection of two basis elements, two members of beta, then there must exist some third basis element, some third member of beta, such that X is in that third basis element, and that basis element is a subset of the intersection of the two initial basis elements. So the picture we have for that is if I have B1 here, I have B2 here, and I know that X is something in their intersection, there has to be some third B3 such that X is in B3 and B3 is a subset of the intersection of B1 and B2. So remember, B1, B2, B3, these are all basis elements. These are all members of beta, right? Okay.
Is X the topology?
No, X is the set that we are defining a basis on. We're going to use our basis to generate a topology on X.
Right, okay.
Right. So that's the exact next thing. What is a topology generated by a basis? The topology generated by a basis is the empty set, every basis element, and every union of basis elements. So if I grab some random set, and I'm wondering, is this set generated by the topology, or generated by the basis? I check three things. Is the set I'm talking about empty? If it is, we're open. Second thing I check, is the set I'm talking about a basis element? If it is, we're open. Third thing I check, does the set I have, can it be represented as a union of basis elements? If it can be, it's open. Otherwise, it's not open. So if it satisfies one of these three conditions, either it's the empty set, it's a basis element, or it's a union of basis elements, then it's open. Otherwise, it's not open. That is what we mean by the topology generated by a basis. You remember the little analogy we had for it with the Lego blocks?
Vaguely.
Vaguely? Maybe it's not useful. I don't know if it is. So, what is nice about having a basis versus explicitly stating a topology? With a basis, we just say, rather than having to enumerate everything in the topology, we just enumerate the basis elements, and we say, and anything these basis elements can create through unions is also in the topology. So imagine the topology we wanted was all Lego structures. I can make my basis elements each individual Lego piece. Right? There's only finitely many Lego pieces, but there's infinite Lego structures I can create, but there's a finite number of Lego pieces. So if I call each one of those Lego pieces a basis element, then the topology, all possible Lego structures, is what can be created from putting those basis elements together. Right?
Yeah.
So it gives us a way of reducing a topology to just fundamental building blocks, fundamental basis units. Another place you might have seen it is component well, never mind. That's more confusing than it would probably help. Never mind. Feel like we're good with the basis? And the topology a basis generates? Any questions before we just continue? Oh, some more recap. That we've already gone over. So we've talked about the standard topology on R. What was the standard topology on R? It's the topology generated by the basis of all open intervals. Let's look at an example. Is this an open set on R? Just the set containing 0 is open?
I don't know.
Okay, if we don't know, let's start with ones that are more obvious. 0, comma 1. The interval from 0 to 1. Is that open on R?
Yes.
Yes, how do you know? It's a basis element. What is the basis? The basis is all possible open intervals. Any open interval you can think of. That's a basis element.
Okay.
What's the topology that generates? The standard topology. And it's the empty set, any open interval, or any union of open intervals. Make sense? So this is open, yes, because it's a basis element. What about -3 to 3 union with 1 to 5?
Yeah. Yeah. Yeah.
Yeah. How do you know?
They're both elements of the basis.
Yeah, you can view these as two basis elements, and this is a union of two basis elements. Or you can say, well, that's really the same thing as the interval -3 to 5, which is a basis element. Right? Okay. What about R? Is that an open set?
Yeah. Seems like it.
Yeah. We can union up all the open intervals x minus 1, x plus 1 for all x in R.
Yeah.
There we go. Union of basis elements. Okay. Is this open?
Yeah.
How do you know?
Empty set.
Empty set is always open when we're talking about topology generated by basis, by definition. Okay, now let's go back to the one I gave you before. The set containing 0. Is that open?
I don't know because
Does
it's
it
not
seem
really
like
an
it?
interval.
No, it's not an interval. So it's not the empty set, right?
Yeah.
It's not an open interval, right?
Right.
Can we get a union of open intervals to get that thing?
No.
No, because every interval has infinite elements, and unioning can only make it bigger. This is a finite number of elements. You know right out the door that any finite set is not open, except for the empty set, right?
Yeah.
So another one. 1, 2, 3. 3. Is that open?
No.
No, because it's finite. There's no way that it's not an open interval. Can this be represented as a union of open intervals? No. An open interval has infinite elements. A union of open intervals then has infinite elements. Does this have infinite elements?
Wait,
Then it for sure cannot be a union of open intervals.
how does an open interval have infinite elements?
Number line. Pick a starting spot, call it A. Pick an ending spot, call it B. What's the open interval? It's all the numbers between A and B. How many are there? Infinite.
Okay.
As long as B is greater than A. They're not the same number. B has to be a bigger number than A. Right?
Yeah.
It'd be easy, real easy to prove that there's infinite things in there, right? Because you can always just take the midpoint of them, that's in there. Take the midpoint of the midpoint, that's in there. Take the midpoint of those, that's in there. You can prove this inductively like that, right? So, every open interval has infinite elements. Okay, let's see another one. Is this in there? No?
Yeah.
No, it's not. There's no way to represent a closed interval like that as a union of open intervals.
Oh, yeah.
Right?
Yeah.
Because an open interval will never include the endpoints. And so I can't union them up, and get closer and closer to 3. I could get closer and closer to 3, but I'll never actually get 3 in there.
Right.
Right? We never include the endpoints in an open interval. So here's an example of something that's not open. What about this? And we actually give it one. There we go. Or we remove one. So now this is open, right?
No.
Yeah.
No, we couldn't get the 0 in there. You can't union open intervals and eventually get to 0. Right? This is all just establishing intuition. We're not proving anything here. I think we'll eventually get to a proof that closed intervals are not open. Maybe it was given as a homework problem. I don't know. Okay, standard topology on R. The topology generated by the set of all open intervals. Right? Now, standard topology on R squared. What's R squared?
It's a plane, pretty much.
Yeah, you think about it as a plane. It's real numbers crossed with the real numbers.
Yes.
It's a set of all ordered pairs of real numbers. Right? R cross R. Remember how to do the cross product of two sets?
Yeah.
Okay. So we went over 2 things to help us make sure we understand what this topology is. So first we introduced the distance formula. This was at the very end last time, right?
Yeah.
We said the distance between point P and point Q is, and I'm just going to use sub 1 to mean its first coordinate and 2 to mean its second coordinate.
Right.
So the distance between P and Q is P's first coordinate minus Q's first coordinate squared plus P's second coordinate minus Q's second coordinate squared. And we proved that real quick just using the Pythagorean Theorem, right?
Yeah.
So that's what we mean by the distance between 2 points in R2. Then we defined an open ball centered at X with radius R is a set of all points in R2 within R of X. All the points Y whose distance from X is less than R. Here's x. R is this. So we've got an open ball not including the border. We're saying it's all the points, doesn't matter which point you pick in here, all the points whose distance from x is less than r. Right?
Yeah.
So a point here is in it, because the distance from here to x is less than r. A point here is not in
But
there.
it doesn't include all
It doesn't include it. It's less than. Not less than or equal. Less than. It's called an open ball. This is the last thing we went over last time, right?
Okay.
And then, so that's what an open ball is. So now what is our basis for the standard topology on R squared? Our basis is a set of all possible open balls. Right? Just like our basis on the standard topology was a set of all possible open intervals, now our topology on R squared is all possible open balls. You with me?
What?
Let's do an example. So here's R squared, the whiteboard, right? Maybe draw a quick coordinate system to help us be comfortable with it. Now I'm going to pick some set of points in there. I picked the points inside this shape, not including its boundary. So we're talking about these points not including its boundary. Is that an open set on R squared?
Yes.
Yes, because we could represent that with a bunch of unioning up a bunch of little open balls around a bunch of points inside of there, right?
Yeah.
Let's do a really simple one. What if I make a circle there, and I'm talking about all the points inside that circle, not including its border. Is that open in R2
Yeah.
with the standard topology? Yes, it's a basis element. Another one that we talked about last time. What about if I take a half plane? So I do dotted line down, and I take all the points over here.
Yeah.
Is that open? Yes. What about if I come down over here and do all these as well? Yes. What happens if I come across dot here and also include these as well?
Mm-hmm.
What if I do everything except for that square?
Yeah.
Yeah. What about everything except for this point? We're missing one point. That's it. Is that open?
Yeah.
Yeah. We take this half plane, union with this half plane, union with this half plane, union with this half plane. The only thing we missed is that point. Right?
Yeah.
So what were you saying with that third bullet point underneath standard on R squared? What does that mean?
This is the basis.
Okay.
So the basis for R squared is the set of all possible open balls you can make.
Oh, okay.
Any radius, any point in R2, create an open ball around it with that radius. That is our basis element. Any one you can do, those are all our basis elements. Right? Good with that? So that's what we mean by the standard topology on R2.
I don't understand how R2 is R cross R.
That's our definition of this symbol. This isn't R squared. When we write R2, that's shorthand for R cross R, as in the set cross product.
Oh, okay.
So it's just notation, and yeah. So yeah, this is not an exponent, this is a symbol for shorthand writing this.
Would R3 be three-dimensional?
Yep. We use the notation R to the n to mean R cross R n times. Okay, and if we continued, by the way, and we wanted to talk about the standard topology in R3, that would be the topology generated by the basis of all open spheres. And you'll notice that we could redefine this basis as each open interval AB can be represented as a one-dimensional ball centered at some point, right? AB, so if I take the real number line, I pick A and I pick B, so we're talking about this open interval, right? That's the same thing as the one-dimensional ball centered at this point, with half that distance as its radius. So these are just one-dimensional balls, these are just two-dimensional balls, and when we're talking about in 3 dimensions, we call them three-dimensional balls. So in general, that's how we're going to talk about the standard topology on Rn. This topology generated from what do we call them? I just lost it. From the n-dimensional balls. So the basis for the standard topology on Rn is all possible n-dimensional balls that you can get of any radius centered at any point in the set we're talking about. That's what we say in general. Okay, so enough recap, let's actually prove some new stuff. So last time, all we really did was prove that a basis does in fact generate a topology, right? So let's see what we're proving first. Theorem 1.9, let beta be a basis on X, that's big X, so this is a set, and we'll use little x to talk about elements. Then U is open, or in the topology generated by beta, U is open if and only if, for every little x in U, there exists some basis element, such that X is in that basis element, and that basis element is a subset of U. Kind of dense, but once you understand what it's saying, it almost feels a little obvious at that point. So a set is open if and only if, for every point in the set, you can find a basis element around that point. That's also a subset of the initial set. Maybe draw a picture real quick. Here's U. U is open if and only if, for every x, pick some random x in there, there exists a b sub x around it, such that x is in b sub x is a basis element, and b sub x is a subset of U. If that's true for every x in U, any x you pick, you can do this, then X is open. That's what we're going to prove first. Oh no, we're going to prove that if X is open, then this is true, and then we'll do the inverse. So, go this way first. Let U be some open set, and let X be some element in U. Now, if U is open, what do we know about it?
It's in the topology.
It's in the topology generated by beta.
It has a basis element.
How do we know it's the
Not
topology
necessarily.
generated by beta?
Oh, that's the topology we're talking about. It's implied.
Oh.
Let beta be a basis on X, then U is open, or in the topology generated by beta, if and only if this is true. Okay, so we know that U is open, or U is in the topology generated by beta, and we're trying to use that information to show that for every point in U, there must be some basis element containing that point that's a subset of U. That's what we're trying to show. So if I know that U is open, I know that U is generated by beta, this basis, right? Now if U is generated by beta, what does that mean? It means U is either empty, U is a basis element, or U is a union of basis elements, right? Now we know that U is not empty. How do I know that?
Because there's X.
By assumption. Let U be some open set and let X in U. The empty set case we're going to say is trivial and not bother with it. Okay. So if X is in U, then what does that mean? U's a union of basis elements. So then there must exist, I don't know another way to say it, but I'll almost say exactly what we're trying to prove. Then there must exist some basis element
In beta.
such that X is in that basis element is a subset of U. It is one, possibly the only basis element that makes up U. But there has to be at least one basis element containing X if X is in U. U is just a union of basis elements. X is in U. Therefore, there has to be a basis element containing that point. That is also a subset of U. Does that make sense? Anything weird there? Okay, so that's it for that way. now we go this way. So let's see what this way is. Assume that U is a set such that for all x in U, there exists bx in beta such that x is in bx is a subset of U, right? We're trying to show that if U is a set that has this property, then U is open, if and only if, right? First we showed if U is open, then it has this property. Now we're showing if it has this property, then it's open. Am I losing you in what we're trying to prove?
No.
You're all good? Okay. So assume that U is some set such that for every point in U, there exists some basis element such that x is in that basis element, and that basis element is a subset of U. Then, what lemma are we going to use? What theorem? What am I trying to prove? I'm trying to prove that U is open, right?
Yes.
So I need U to be a union of basis elements. What is U equal to?
What you just wrote on the board.
It's the union of all the b sub x's. I know that the set U has a special property, such that for every element in U, there exists some basis element, such that x is in that basis element, and that basis element is a subset of U. Therefore, U is equal to the union of all those basis elements. The union lemma, right?
Okay.
Remember the union lemma?
Yes, it's been a while.
Yeah. So then U is equal to the union for all little x in U of b sub x. For any little x you pick in U, I can find the basis element containing that point. Union them up, and that gives you U by the union lemma. And since U is equal to a union of basis elements, that gives us U is open. Right? That's what it means to be open. They're either empty or a union of basis elements.
Yeah.
Including the case where you union up one basis element to get it. Any questions there?
Will you go over the union lemma?
The union lemma. So the union lemma was, if I have a set such that, we'll call the set U, since that's what we use up here. So here's a set U. If I have a set U that has a property such that for any x you pick in U, there exists a subset around that point x, call it b sub x, where b sub x is a subset of U. Then, the union of all those b sub x's is U. That was the union lemma.
What if there's just that one b sub x?
Then that b sub x has to contain every x. So it says that for every little x in U,
I thought it was just all the b sub x's for that one.
no, b sub x is changing for every element in there. So if our elements are 1, 2, 3, then we're talking about b sub 1, b sub 2, b sub 3.
That makes sense.
Okay, yeah. Any other questions? Good? You need to look out for a sec before you have a question?
Nope.
You good?
Yep.
Okay. All right, feel free to ask questions to your heart's content. There's no requirement that we need to get through such and such material in a day. So make sure it makes sense. Okay. Now, moving on to a lemma that's going to help us with this theorem. So the book introduces a theorem that says first we're going to prove this lemma. That's why the numbering's weird. But this lemma just helps with this theorem. What are we proving in this lemma? We're proving in this lemma that pick a point x and the open ball around x. So for any open ball you pick a point in there, call it y. we're saying for any open ball you pick and for any point in there, I can create an open ball around this point such that this open ball is a subset of this open ball.
But can't you make the ball bigger than the other ball? Like, can't it go outside of it? So that
We're given some open ball. Here it is. What are we proving? We are proving that for any point in here you pick, doesn't matter, for any point in here you pick, there exists some open ball I can create around this point, such that this open ball is a subset of this open ball. There's a lot of them. There's infinitely many I can pick, but there's at least one.
Okay.
Does that make sense?
Can you read the actual statement and show how that is?
Let x be a point in R2, and let R be any positive number. We're going to use that for the radius.
Okay.
Then for every point in the open ball centered at x with radius r, there exists some epsilon, some other smaller radius. In our case, here's the epsilon.
Oh, okay.
There exists some epsilon, some other small, or some smaller number, such that the open ball centered at y with radius epsilon is a subset of the open ball centered at x with radius r. Okay? You understand what we're trying to prove?
Mm-hmm.
We're given a ball like this and some point y in here. Our job is to construct an open ball centered at this point such that this open ball is a subset of this open ball.
What if epsilon is greater than r? It doesn't say that.
It doesn't say that for any epsilon you pick you can make this true. It says that there is an epsilon you can pick that makes this true.
Okay.
And obviously epsilon has to be smaller than r, right?
Right. Okay.
Well, I guess it could be equal to r in the case where y and x coincide.
Yeah.
Okay, to prove this theorem, we're going to have to use something called the Triangle Inequality. Now, I don't know if you guys have come across it or not before. It's a basic proof in both calculus and geometry. What does the Triangle Inequality say? The Triangle Inequality says that for any triangle you make, the sum of any two sides you pick, this side and this side, is always greater than the remaining side. This distance plus this distance is always greater than this distance. That's the triangle inequality in geometry. Okay? The way that we're going to use that is we're going to say that the distance from this point to this point to this point is always less, or is always greater than the distance just going straight from here to here. So the distance going from A to B to C is always greater than the distance of going just from A to C. And we're going to use that fact. That's called the triangle inequality. It's not something we prove in this class because obviously it's a property of geometry.
Does that work for topology? I thought topology is like a rubber.
We are going to be talking, we're going to be
geometry.
dealing with this on R2.
Okay.
And
So it's like a geometry proof.
yeah, we're getting into a dangerous space here because we're just proving things about what the standard topology has. And the standard topology, it turns out that you could develop geometry on it, but we don't know that yet. We'll come back, it's going to be like chapter 5 when we start getting into metric spaces, and then we'll come back to an idea like this and prove it very generically.
So this same proof works with a rubber, like a rubber plane.
No.
Oh,
This works on R2 with the standard topology
okay.
because it just so happens that that topology gives us the geometry that we know and love. So yeah, it's something that we're assuming to introduce it here to give us a feeling for the standard topology, and we're going to come back to metric spaces, which is where we formally prove this idea. Okay. Containment. Oh, so yeah, our limit. Let's prove our limit. So let's start with an open ball. 1. Let BXR be an open ball and let y in it. So grab some random point y out of our open ball.
Okay.
We need to show that we can construct an open ball centered at y such that that ball is a subset of this ball. Okay?
Okay.
2, maybe, I don't know how many lines I need. Let's see. This is going to seem kind of strange. I'll motivate it here in a second. Well, maybe I'll prove it and then I'll come back and motivate it with the picture. But let y be any positive number, or let epsilon be any positive number. So 0 less than epsilon less than r minus the distance between x and y. So epsilon is
Smaller.
this distance r minus this distance.
Okay.
So whatever distance is left, it's going to basically be this distance. So we're going to make so our open ball always goes exactly to the very edge of the circle, but it doesn't include the edge, right?
Okay.
So let epsilon be some number between those. It doesn't have to go all the way to the edge, but that's the furthest it could go. So let epsilon be any positive number between those. And it remains to show that the ball centered at y with radius epsilon is a subset of the ball centered at x with radius r, right? That's what we need to show, and then we're done.
Mm-hmm.
How am I going to show this as a subset of this? I'm going to grab a random point in here and show it's in here, and then we're done. So let P be any point in B, Y, epsilon. Well, if P is in this ball, what does that mean? Well, then we'll just look at this. Then the distance from X to P, remember, what is this ball? It's a set of all points whose distance is less than r away from X. I grab P, some random point in this ball. If I can show that the distance from X to P is less than r, we're done.
Okay.
Yeah.
Does that make sense?
Mm-hmm.
Okay, so that's what we need to do. So then the distance from X to P is less than, triangle inequality, the distance from less than or equal to the distance from X to Y plus the distance from Y to P. Right? So P some point over here, here's P. We're saying the distance from X to P is less than or equal to the distance from X to Y and then from Y to P.
Okay.
Mm-hmm.
Okay. So then the distance from X to P is less than or equal to the distance from X to Y plus the distance from Y to P, which is less than the distance from X to Y plus epsilon, right? The distance from Y to P has to be less than epsilon because P is in this ball.
Yeah.
Yes.
That makes sense?
No, what you just really said doesn't make sense.
The distance from Y to P has to be less than epsilon because because P is in the open ball centered at Y with radius epsilon.
Oh, and you just added that distance on, so the inequality.
I'm taking this inequality and replacing this with epsilon, which could have only made it bigger.
Yeah.
I see.
And now, that is equal to, that is less than the distance from X to Y. What do I know epsilon is smaller than? I know epsilon is smaller than r minus the distance from X to Y. So, plus r minus, there's a white spot there, that's a long minus sign, the distance from X to Y, which is equal to r.
Yeah.
Okay, so X.
And we're done. So that gives us that the ball at y with radius epsilon is a subset of the ball at x with radius r. Would be nice to have one more line worth of space, but oh well.
Okay.
One more time?
Yeah.
Or you think you got it? One more time through? Okay, let's go through one more time and we'll draw the picture as we go. To try and make sure everything makes sense. Okay. So we start with some arbitrary open ball. We don't know anything about it except for it's an open ball with some radius r centered at some point x. So I got some point x and some open ball around that point with radius r. Now, pick any point in here you want. Doesn't matter. And we're going to call it y. Here's y. Y, we gave it a radius of epsilon. All we know about epsilon is some positive number less than r minus this distance. Right? So take r minus this distance. Therefore, the furthest epsilon can be is from here to the very edge of the circle, right?
Mm-hmm.
But it could also be smaller than that. I just have to make sure whatever I use for epsilon, I don't go bigger than this distance. So here's my possible epsilon. Here's a possible epsilon. Good so far?
Mm-hmm.
Okay. So let this be our ball, be an open ball. We took some random point in there, and then we let epsilon be any number that's less than this distance minus this distance. So it can't be bigger than this distance. And it's not. Okay, we're good so far. Now we're trying to show that this open ball is a subset of this open ball. How are we going to do that? We grab some random point in here, P. Here's P. And we need to show that the distance from x to P is less than r. That's what we're after. If the distance from x to P is less than r, we're good. Because then P is also in this set, and therefore this set is a subset of this set. So this inequality is the whole heart of the proof, showing that this inequality is true. Okay? Now we know that the distance from x to P is less than or equal to the distance from x to y plus the distance from y to P. Right? That's the first step. The distance from x to P is less than or equal to the distance from x to y plus the distance from y to P. That's what I just said.
Mm-hmm.
Now I know that the distance from y to P is less than epsilon.
Yeah.
So I replace the distance from y to P with an epsilon. I could have only made it bigger. Epsilon, by definition, is a number less than r minus the distance from x to y.
Mm-hmm.
So, if I replace epsilon with r minus the distance from x to y, I could have only made it bigger.
Mm-hmm.
So, we only made it bigger. Now simplify r. So the distance from x to P is less than r. Therefore, P is in this open ball. Therefore, this set is a subset of this set. Because we could do this for any P you pick.
Uh-huh.
Okay.
Makes sense.
Yep, makes sense.
All good? Ready to move on to the next one?
Yes.
Okay, so what is the next one saying? Okay, so we just stated that open balls are a basis for a topology on R squared. Now we need to prove that they in fact are a basis. So we've said it, we've been treating it like it's true. Now we're going to prove that the set of all open balls is a basis on R2. How do I show that the set of open balls is a basis on R2? Two things. I need to show that every element in R2 is in some basis element. And I need to show that if I have an element in the intersection of two basis elements, draw a picture because I'm going to say element. Oh, we've got it here. So I need to show this. I need to show that for every x in R2, there exists some basis element such that x is in that basis element. Next, I need to show that if x is in the intersection of two basis elements, then there exists some third basis element such that x is in that third basis element, and that third basis element is a subset of the intersection of those two basis elements. If I can show that that is true with open balls, we're done. They're a basis. And the topology that they generate, we just call it standard topology on R2. So that's what we need to prove. So first I need to prove every point is in some basis element. How am I going to do that? So let x in R2. I need to show that there's a basis element containing x.
How do you do that?
Can you come up with any basis element containing x?
Yeah.
What?
X minus 1 to x plus 1.
That's an open interval.
Is that not a basis element?
We need a circle now,
Oh.
because we're in R2. What ball is it in?
X to R.
X to R.
X plus 1, sorry.
X with radius of
Oh.
Can you just say a word?
I don't know. X to radius of
19, right?
What?
Okay.
Is the open ball centered at X with radius 19 an open ball?
Yeah.
Then it's a basis element. Does it have X in there?
Yes.
Yeah.
Then it's a basis element containing X.
Okay.
So X is in that open ball, which is also in our basis. Right? We just found some basis element containing X. There's infinite basis elements containing X. We just need to find one. There's one.
Okay.
Right? Don't gotta overthink it. Okay. So we showed the first condition. Now I need to show that if two balls are intersecting, if two basis elements are intersecting, or two open balls are intersecting,
And there's also pieces.
then for any point in that intersection, I can find a third little ball inside the intersection as well. Right? So picture of what we need to prove now. Need to make these open balls. So here's two open balls that intersect, right? And here's a point in their intersection. I need to show that if I have two balls that intersect, then for any point in their intersection, I can construct an open ball around that point, such that that open ball is a subset of their intersection.
Yeah.
I'm doing dotted lines, but I hope you can see the circles. They don't include their boundary, but I'm just trying to help you see them, right? So those don't include those boundaries, just two open balls intersecting.
Okay.
So, let B, I'll call it just x1, comma, r1 intersect the ball at x2, r2. Let these two basis elements have some intersection. With me so far?
Yep.
So let these be two open balls such that their intersection is not empty. I don't know why I'm slamming so much, am I right? So if it's not empty, then we can grab something in there.
Yeah.
So and we'll just use x for the thing that's actually in there. So let x be something in their intersection. I was trying to come up with a way to not have to write these twice. So let x in their intersection. Okay. So now from our previous theorem, I know that I can, maybe just write it. From that thing over there, there exists epsilon 1 and epsilon 2 such that, why am I sliding down so much? That was intersection at x2 radius r2. Okay, so from what we have over there, there exists two positive numbers epsilon such that the ball centered at x with radius epsilon 1 is a subset of the ball centered at x1 with r1 as its radius, and the ball centered at x with epsilon 2 as its radius is a subset of the ball centered at x2 with r2 as its radius. Right?
Don't you mean from our lemma?
Yeah, from,
there.
oh, it's up there. I thought it was over here. Yeah, from that lemma.
Okay.
So that lemma said, anytime you have an open ball and a point inside an open ball, I can construct a smaller open ball around that point so that the smaller ball is a subset of the bigger ball. So I can do that with the first ball,
Yeah.
and the radius that one has is epsilon 1. I can do that with the second ball, and the radius that one has is epsilon 2.
Yeah.
So 5, let epsilon now equal the minimum of epsilon 1, epsilon 2. And observe that the ball centered at x with radius epsilon is a subset of the ball centered at x1 with radius r1, and the ball centered at x with radius epsilon is a subset of the ball centered at x2 with radius r2, which gives us that the ball centered at x with radius epsilon is a subset of their intersection. And therefore its basis. Therefore beta is basis. And we're done. Any questions there?
Yeah. I don't get it.
You
How?
don't get it?
Like, why?
You got that the ball, you
get
got that
it.
there's epsilon 1 and epsilon 2,
Yes.
such that the ball centered at x with radius epsilon 1 is a subset of this, and the ball centered at x with radius epsilon 2 is a subset of this, right?
Yes.
Notice if I make the radius smaller, I'm just excluding points. I'm not including points.
Yeah.
So if the ball centered at x with epsilon 1 is a subset of this, then if I make epsilon 1 smaller, it's still a subset.
Yeah.
Similarly, here, the ball centered at x with radius epsilon 2 is a subset of this. Therefore, if I make epsilon 2 smaller, this is still true. So if I make epsilon the minimum of these two numbers, I could have only made it smaller. I couldn't have made it bigger.
What do you mean by the minimum of those two?
Epsilon 1 and epsilon 2 are positive numbers.
Yes.
One of them is smaller than the other. Or they're the same.
Okay. So
Let
you're-
epsilon be the minimum of those two. Oh, sorry, are you not used to this minimum notation? Okay, just common notation. This is not a set or anything. You could view it that, a minimum function on a set of things if you want. But minimum and then brackets and then listed elements means just the smallest thing of all the things we put between those brackets. Common notation, man.
Okay.
Sorry about that.
Can you draw a picture of this?
Sure. So we've got, these are open balls, but I'm going to give them a closed border because, just let me see them. We've got two, maybe one of them is way bigger than the other. Two open balls with some intersection and some point in there. Now, there's an open ball I can make around this point. That makes it a subset of this circle. That's not really a circle, geez. It's going to be hard to see it correctly if I don't draw my circles at least halfway decent. How hard would it be to use this real quick? So we'll do one circle. And we don't really need the whole thing, we just need the intersection part. And we'll do some other circle. And we don't really need the whole thing, we just need some intersection part. Wow, that was terrible. Okay. Terrible, terrible. Zoomed in picture where two circles intersect, right?
Okay.
Now we're saying that for any point in here you pick, I can create a circle around this point so that it is completely contained within this ball, right?
Yeah.
And I can create some other circle around this point so it's completely contained within this ball.
Uh-huh.
The smaller of those two circles is always going to be within both.
Well, it seems to me like it depends on the degree of their intersection. Like if it's barely on the edge.
So here's my point, right? There's some max number that I can't go past. So any radius more than this keeps it in the big circle, right?
Yeah.
And any radius more than this keeps it in this circle, right?
Yes.
So any radius that's smaller than the minimum of both those has to be in both circles.
Radius is smaller than minimum.
But your proof doesn't say that. It's saying the minimum of the big radius.
No, epsilon is the radius of the open ball around this. So I'm saying that there's two open balls I can create around this. So let's say one's really small, and then one's bigger, like that.
Oh, okay.
So the bigger one happens to go outside of this circle. So this radius right here, we'll call epsilon 1. And this one, this is B1. And this other ball over here is B2. And then this radius right here is epsilon 2. So the smaller radius will always keep it in both balls.
Okay. That makes sense.
The bigger radius might have only been inside one ball. It was for sure in one ball, maybe not the other. But the smaller of the two radiuses is for sure in both balls.
Are you sure about that? Because
I'm positive.
I'm confused because
As I make the radius smaller, I can't get inside a ball that I wasn't already inside. Or I can't get outside a ball if I'm already inside of it. So for radius epsilon 1, I'm always within one ball for sure. Right?
Uh-huh.
With radius epsilon 2, I'm always within the other ball for sure. So if I only make it smaller, then I'm for sure in both.
okay, what I'm confused about is couldn't you just have two balls that are both in both of the balls?
Two balls that are always within both.
Yes, that are in the intersection, but it includes the outside of the intersection.
I cannot create a small ball that is, I can't create a ball centered at this point that is inside this circle and outside this circle, and an open ball centered at this point that's inside this circle and outside this circle. That's an impossible picture. Because imagine I start out with a really, really tiny radius. Right? And we're inside both, right? As I make it bigger and make it bigger and make it bigger, I eventually get outside one ball.
Yeah.
Right?
Mm-hmm.
And then outside the other. I can't get outside one and still inside the other, and then suddenly, okay, now get outside that one and inside the other. Once I'm outside one, I'm outside it. Making the radius bigger just keeps me outside. The only way to get back inside is to make the radius smaller. So I can't, if you're saying, can I have a picture like this? So you're saying, can I have a picture, here's the point, where I've got this open ball, and the other open ball is like this, right? You're saying, can't we do that?
Yeah.
And the reason is no, they have to be centered at this point.
Okay.
They have to be centered there. And so we can only grow out from that point.
Okay.
You feel like you got it?
Yeah. I thought that epsilon 1 was like a radius of one of the balls, but that makes sense.
It's a radius not of one of the balls we started with, but of one of the balls that we're guaranteed exist.
Okay.
So I'm guaranteed that there is some small radius I can do, epsilon 1, around that thing.
Yeah.
That makes it a subset of this ball. And another small radius I can do that makes a subset of this ball. But the radius in this picture, whatever radius works for my bigger ball, also works for my littler ball.
Yeah.
For that point. It can change from point to point.
Okay.
Nice go.
Thanks.
All right. Did we finish it? I think we finished it, right?
Yeah,
Yeah.
approved it.
Makes sense.
Okay, so that's a basis. Any questions, other questions, anything confusing? Are we ready to move on to the next proof? Yes to an or question.
Yes.
Should just say yes, Tim.
Okay. So now, that's still plugged in. Okay, and we should be good. Okay, so now this. And before I stand up and do it, let's give intuition for what I was talking about. So now we talked about open balls and what open balls generate. Next we're going to talk about open rectangles. What's an open rectangle? Exactly what you think. A rectangle. That's open. So it's all the points inside. How are we going to describe an open rectangle? It's a cross product of two open intervals. So if I take this open interval and cross it with this open interval, it gives me this rectangle. Let me draw it in a coordinate system to help you make sense of it.
Yeah, that makes sense.
So we've got our xy plane. And I'm saying pick any open interval on the x-axis. Okay, we picked this one. Now pick any open interval on the y-axis. Okay, we picked this one. Now the cross product of this with this is going to be all the points whose first element come from this set and whose second element come from this set.
Mm-hmm.
These points. And we created an open rectangle. Make sense?
Yep.
I may call this point A, this point B, this point
But you don't actually have
C,
the outside.
and this point D. Yeah, it doesn't include the border. It's an open rectangle, because these are open intervals.
Okay.
Right?
Mm-hmm.
Okay. So now here's what we're going to prove. If you take the basis of all open rectangles, A, that is a basis for a topology. And B, the topology it generates is a standard topology. So we just barely talked about all these open balls, right?
Yeah.
Where he says, take the collection of all possible open balls. We said, that is a basis on R2, we just proved it. And we call that the standard topology on R2 now.
Yeah.
So now I'm going to take the collection of all open rectangles. I'm going to prove that that is a basis. And then I'm going to prove that the topology it generates is this exact same topology, the standard topology.
Oh, okay.
The idea that we're getting at is that you can pick any open shape you want, all the shapes like that. All the shapes like that, somehow you have their center defined, of any radius you want, any weird random shape you want. The basis element of all of the collection of all possible shapes like that that you can make generates a standard topology. It doesn't matter what shape you use.
On R.
On R2. Yeah, we're doing this for R2. That's what we're ultimately saying.
Okay.
But that's what we're working up to. That's what our last proof is going to help us get. This is our second to last proof. Okay. So, first first thing I need to show is that the collection of all open rectangles is a basis. That's the first thing we're showing.
I have one question.
Yep.
So your standard on R, if its basis elements are open intervals, then are the elements of R open intervals?
The elements?
So we're talking about the standard topology on R2.
No, on R. I'm talking about R.
On R.
I
So the
know
standard
the
topology
real
on
numbers,
R
but
is
the-
open intervals.
With the way that you... Okay, I'm confused. If the basis of some set is open intervals, isn't that set made up of open intervals too?
No, R is not open intervals. R is just all real numbers.
Well, I know that, but the way that you were explaining it...
A basis is collections of subsets of the set you're talking about. So when we're talking about the set R, our basis elements are subsets of R that satisfy two properties.
Okay, I thought R was some sort of topology.
No, R would always be a member of a topology on it, but the smallest possible topology we can create on R is this. This is the smallest possible topology on R.
Okay.
So R itself can't be a topology.
Alright.
Or it can't be a topology on R.
And the elements are just values, they're not open or, right?
Yeah, the elements of R are just real numbers. That's what we mean by R, the set of all real numbers. And probably should have said, like when I did this here, anytime I do something greater than 0, I'm always talking about a real number. I didn't specify R as a real number here, but
Okay.
positive real number is why I went there. So another way I could have written this is R in the positive reals, if you prefer. Good? Okay, so that's what we're proving here. First thing we're proving is that the set of all open rectangles is a basis on R2.
Okay.
The set of all open rectangles is a basis on R2.
And we defined open rectangles as what you just did?
Yeah, we're not gonna say open rectangle, we're gonna say beta equal to the cross product of all possible open intervals. It's just that's what we mean by an open rectangle, so I'm gonna use that terminology.
Okay.
So beta equal to the set of all possible Cartesian products of open intervals is a basis on R squared, and the topology tau it generates is a standard topology on R2.
So first
And I'm
we're
going to
trying
call
prove
that tau
it's a
sub
basis.
s.
What
In
you
this
talking about, a standard topology one more time? I know you already did it.
So
Like, what's the significance of that?
it's just the name of a topology. So we talked about the basis of all open balls. We proved that the collection of all open balls is a basis, right here. It's a basis, which means it generates a topology. We already proved that.
On R.
Whatever topology that generates, we're just going to call that the standard topology.
Okay.
Now we're going to show that the topology that this thing generates, first we're going to prove it also generates a topology. We just need to show it's a basis and we're done. Then the next part is we're going to show that the topology it generates is the standard topology. Now I'm not going to go back and forth. I'll probably just show that everything in the standard topology is also in here, and the other way to prove, you'll see how to do it by the time we get there.
Okay.
Totally.
You'll see. Okay, so first let's prove that this thing is a basis. So 1, let beta equal the set A, B cross C, D such that A is some real number less than B and C is some real number less than D. And we'll grab something in R2. And let X be anything in R2, some point. First thing I need to do to show that beta is a basis is I need to show that X is in some basis element, right? What does it mean to be a basis? I'm trying to prove it's a basis. What does it mean to be a basis? It means that for every point in R2, there exists a basis element containing that point.
Yes.
And then I need to show that anytime two basis elements contain a point, there exists a third basis element that's a subset of their intersection.
Yes.
Yes.
Okay, So first thing I need to do is find a basis element containing x. So let beta be this whole thing and let x be some point in R2. Then, what's my basis element containing x? So x is in what basis element? We'll call x's first coordinate x1 and x's second coordinate x2.
Oh, okay. Then it would be like x1 minus 1 to x1 plus 1. And then you do the same for y coordinate. Or the y interval.
Perfect. Everyone follow that? Or do we need a picture?
We might need a picture.
Okay, so we've got our xy plane, and we just pick some random point out of there, x. Right? And I'm calling x's x coordinate, x1. I'm calling x's y coordinate, x2. And x just means the point. With me so far?
Yeah.
Okay.
So she just said, okay, so take x1, go 1 unit to the left and 1 unit to the right, and create an open interval. So this is the open interval from x1 minus 1 to x1 plus 1. So x1, here's x1. x1 minus 1, I don't know where it is, but it's 1 unit this way, right? So somewhere over here. And x1 plus 1 is 1 unit to the right, somewhere over there. Here's this open interval.
Okay.
Same thing, create an open interval over here. Right?
Yeah.
Now take their cross product. What is their cross product? Their cross product is all the points in this rectangle, not including the boundary. Right? It's all the ordered pairs whose left-hand element came from here and whose right-hand element came from here. Right?
Okay.
So x is obviously in there. Make sense?
Yeah.
Okay. So wonderful. So we just barely showed that for any point in R2 you pick, we can find a basis element containing that point.
Yeah.
Right? Now I need to let two basis elements have an intersection such that x is in their intersection. And so there's a third basis element just containing that x. Or sorry, third basis element, that's their subset. So maybe draw a picture for how I'm going to do this one real quick and then we'll go write it out. So I've got two basis elements that intersect. I think I'm just going to use A1, B1, C1, D1, and then A2, B2, C2, D2. So try and be a little better here. So we're going to have something that looks like, here's A1, here's B1. There's a lot of different ways that this picture could look, but I'll just draw one potential way. C1, D1. And then we're going to have maybe A2's over here, maybe B2's right here, and maybe C2's right here, and maybe D2's right here.
Okay.
So let's draw our two sets. Kind of wish I could do these different colors. Should have done this on the whiteboard. So the first set is A1, B1 crossed with C1, D1. So the first set is,
I think he has colored chalk.
so our first basis element is this rectangle. Maybe I'll just draw in the rectangle even though you know it doesn't include the boundary, right?
Yeah.
So here's our first open rectangle. Our second open rectangle looks like this. Something like that, right? Sorry, that was terrible. So we have two open rectangles that intersect. What I need to do is, for any point in there, I need to know that there's an open rectangle containing this point. Now obviously there's going to be an open rectangle containing the point. Just the intersection of the two open rectangles is always going to be an open rectangle. Right?
Yeah.
And what the intersection is always going to be is I'm going to write a big line here, but don't lose track of the logic. It's going to be the minimum of A1, A2 to the minimum, or to, sorry, this is max. Max of that to the min of B1, B2. That interval crossed with, and repeat, the max of C1, C2 to the minimum of D1, comma, D2. So let's write it out for our specific case.
Wouldn't it be the min of both?
Now, max for the lower bound one, min for the upper bound one. So let's see. First I need to take the max of A1, A2. What's bigger, A1 or A2?
A1.
A1. So I'm saying in this case it's going to be A1, 2. What's smaller out of these?
A2.
B2. So it's going to be A1, B2 crossed with, what's bigger out of these? C1. And what's smaller out of these?
D1.
D1. I'm saying here's the open rectangle that's going to have your point and is going to be a subset of the intersection because it is the intersection.
Yeah.
That is exactly, let's see, we said A1 to B2, so that's this, crossed with C1 to D1, this, which is exactly this rectangle, their intersection, right?
Yeah. Makes sense.
Okay, that's the whole trick to showing that it's a basis. Just writing out the algebra now. So, now, let x be something in A1, B1 cross C1, comma, D1 intersect A2, B2 cross C2, B2. Okay, so let x be something in their intersection. What does that give me? That gives me that A1 is less than x is less than x1, its first coordinate, less than B1, and C1 is less than x2 is less than D1, and get confused with all my subscripts. And A2 is less than x1 is less than B2, and C2 is less than x2 is less than D2. Right? All I'm saying is that whatever x is, it has to be, its x coordinate has to be bigger than A1 and bigger than A2. And its x coordinate has to be smaller than B1 and smaller than B2. And its y coordinate has to be greater than C1 and greater than C2. And it has to be smaller than D1 and smaller than D2. By definition of it being in these intervals, right?
Mm-hmm.
In other words, what does it mean for x to be? If x is in these two cross together, then x1, its x coordinate, has to be in A1, B1, right? Which is the same thing as A1 is less than x1 is less than B1. That's why I'm just doing over and over again, expanding this whole thing out. So, you good with this whole line so far?
Yeah.
Okay, now I'm just going to define A, B, C, and D to be the mins and max, exactly what I said down here, and then it's going to be satisfy those inequalities, therefore it's in that intersection. Right? Should I even bother writing this, or do you think you got it?
I think it's obvious. Just point to it or something.
Write it or continue? want to see
We
that
have
explicitly?
something else to prove after this, right?
Yeah, we need to prove that the topology it generates is a standard topology.
I think we understand this.
Just write like a little
Right, all I'm going to explain from here on out is, therefore when you do this, take the min and max this way,
It's a basis element.
x is going to be in there, and this is always a subset of the other sets,
And so therefore it's the basis element.
and therefore it's a basis element. So, blah, 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 therefore beta is a basis element. Is a basis, I mean. Now generate some topology T. Some topology tau. We just need to name it so that we can talk about it later in the proof. Should have just split this into two proofs. I don't know why he doesn't. Should have proved first that it is a basis and then that it generates a standard topology, but we'll move on now. So now we gotta erase this so that we can continue filling it out. So, what remains to show? What remains to show is that the topology tau that this thing generates, whatever that tau is in fact the standard topology. Now I'm going to show that the standard topology is a subset of this thing, showing that this thing is a subset of the standard topology is very similar. We'll go over the picture for how you do that, and then I'll actually go through and do that.
I have
Okay.
a question.
Go ahead.
Over there you say standard on R squared. Is that you defining the standard topology on R squared?
Yep.
Okay.
So what is the standard topology on R squared? It is the topology generated by the basis of open circles, or open balls, sorry.
Okay.
So take the set of all open balls as a basis, the topology it generates, we're calling whatever that topology is, the standard topology. And now we're going to show whatever that topology is, everything in it is also in this topology. Okay?
And everything in this topology is also in.
Right, but we're just going to prove it one way, going the other way, very similar. So here's what I'm going to start with. I'm going to start with some, there's my U. I'm going to start with some open set in the standard topology, and I need to show it's in this topology. And hint, hint, what am I going to use? I'm going to use the union lemma. I'm going to show that for any point in here you pick, I can find some subset around that point that is a rectangle around that point, and that open rectangle is also going to be a subset of U. Therefore, the union of all those rectangles gives me U. Therefore, U is the union of open rectangles. Therefore, U is in the topology generated by beta. Right? And going the other way is a similar way. Now, if we start out with some open set U inside this topology, then I need to show for every point in there. I can find some open circle around that point. And therefore, the union of all those open circles gives me this set by the union lemma. And since then I can make this set a union of a bunch of open balls, it's in the standard topology. So I'm going to use this picture, but going the other way just uses that picture. You with me? So that's all. That's why I'm only going to prove one way, not the other. Make sense? So how am I going to do this? I'm going to start by saying, okay, pick any point you want, x in U. Now I know since U is in the standard topology, it's a union of open balls. Right?
Yes.
So I know that whatever that x is, I won't mark it, there's x. Whatever it is, there's an open ball around that point that's a subset of U. And then I know how to inscribe a square inside a ball, which will still contain the center of the circle. So x will be inside an open square, which is an open rectangle. You with me? Should we say that one more time? U is going to be any random open set. You're going to pick any random point in there, x. Since U is in the standard topology, I know that it has an open ball around it. Right? A radius r. We don't know. Some radius r, centered at x. Then, I'm going to use the fact that I know that I can create an open ball of some radius r around it to construct an open rectangle around it that's completely inside the circle. And since my rectangle is inside the circle, and I know that my circle is inside of U, my rectangle is inside of U. Therefore, I found a subset. For every x in U, I found an open square, or an open rectangle around that point that's a subset of U. Therefore, union up all those open rectangles gives you U. Therefore, U is in this topology.
Okay.
Okay, that's big picture what we're going to do. All right, so let's do it. So let U be any open set in the standard topology, comma, and let X be any point in U. Are you getting confused by me using X over and over again, or are you fine?
It's just an arbitrary element.
Yeah, just an arbitrary element in U has nothing to do with what we've been calling X up here.
Okay.
Completely new arbitrary point. Then there must exist some ball centered at X with some radius R. Maybe I'll say there must exist some radius such that. So then there must exist some R greater than 0, some radius, some positive number, such that the ball centered at X with that radius is a subset of U. Okay?
Yep.
Now we're just going to get into some technical algebra for a second. You can get lost in the math, but with the picture, it'll make perfect sense. So we've got a circle X with radius R, right? I need to inscribe a square in there. How am I going to do that? So we're going to call these points x1, comma, x2. I'm going to make a square in there. I'm going to talk about this square. To do that, I need to get these points on the square, right? So I know that we'll put our R here. This is the radius R, right?
Yeah.
So then this distance is going to be
R divided by the square root.
R over the square root of 2. R over the square root of 2. So I'll just mark this point. The x-coordinate of this point then is x1 plus R over the square root of 2. And then its y point is going to be the exact same thing, right? x2 plus R over square root of 2. And we're just going to take the 4 different combinations. Is anyone getting confused how I'm calculating this point?
Yeah.
You are confused? Because you shook your head and said yeah. Okay. So let's go over that real quick then. So when I create this square, let's just draw that triangle out real quick. So I've got some triangle, radius R. I know that this is a right angle, right? And I know this is a 45 and this is a 45. So the Pythagorean Theorem holds up, right? So call this side A. Whatever this side is, this side has to be the same thing A, right?
It has to be.
Yeah, this side and this side have to be the same big. This and this have to be the same big. Because this is a 90, this is a 45, and these angles are the same. These angles are congruent. Therefore, these sides have to be congruent. Pons Asinorum,
What did you say?
that's the name of the theorem.
Okay.
If you have a similar triangle, if the base angles are the same, then the sides are the same.
Oh, yeah.
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 Okay, so you with me?
Yes.
Okay, so this is A and this is A, whatever it is, and this is R, right? Now we're trying to describe A in terms of R. I'm saying A is R over the square root of 2. And we get that from Pythagorean Theorem. So I know that this squared plus this squared equals this squared. So I know A squared plus A squared is equal to R squared. Or in other words, 2A squared is equal to R squared. Or in other words, the square root of 2A squared is equal to R. They're all positive numbers, so we don't need to worry about plus or minus, right? Or the square root of 2 times the square root of A squared is equal to R. Or the square root of 2 times A is equal to R. Or A is equal to R over the square root of 2.
Okay.
So, if this is R, then the length of this has to be R over the square root of 2. And the length of this has to be R over the square root of 2. So if this coordinate in the xy plane now we call x1, comma x2, that's its x and y coordinate, then this point right here is x1 plus r over the square root of 2, and its y coordinate is what x2 plus r over the square root of 2. And then down here is just going to be plus on the x minus on the y. This is going to be minus on both. This is going to be minus on the x plus on the y. But the exact same thing everywhere. You follow that?
Yeah.
Anything weird?
But why are you creating a square?
I need to create an open rectangle that is a subset of U. So back to what we were doing. So looks like we got lost in the details a little bit. So let's go back to what we're doing. So I'm starting out with some open set U. I know nothing about what U looks like. But maybe it's something like that. Who knows? I know nothing about what U looks like. I need to find, for every point x in U, any point x in U you pick, I need to be able to create an open rectangle around that point such that that open rectangle is a subset of U. I need to be able to do that for every point in U. If I can do that, then U is the union of those open rectangles.
Yeah.
And therefore, U can be expressed as a union of open rectangles, or in other words, U is in that topology generated by that basis. So tau is a topology generated by all our open rectangles. I grab U, which is a random thing in the standard topology, and I'm showing that U is in there. So if I can show that this is true for U, we're done. Now I know that U is in the standard topology, so I know that U is a union of basis elements in the standard topology. What are these basis units in the standard topology? Open balls. So if x is a point in U, I know that there's some open ball around it. Now, using what we just talked about over there, I know how to create an open square inside that open ball that still contains the center. So there we go. So for every point x, I just barely found an open rectangle that contains it, and we're done. You follow that? So now let's just write it out. And I'm going to pull these numbers out of the blue, but they're explained over there. So then, x is in, let's see how we can describe this. It's going to be x1 minus r over the square root of 2 to x1 plus r over the square root of 2 crossed with x2 minus r over the square root of 2 plus, comma, 2x2 plus r over the square root of 2, which is a subset of the open ball. Right? So, that gives me that this thing, I should have named it, so I don't have to write again, then x is in the intervals, or the rectangle sub x, equal to that thing. So we'll call R sub x the open rectangle containing x. And so for every x, you can create an R sub x this way. Because you know that for every x, there is some open ball around it. So since for every x there is an open ball, then for every x you can create this R sub x, this open rectangle.
Except aren't you just crossing 2 points? Don't you have to cross?
No, these are now open intervals.
You set x equals.
This is the open interval from here to here, crossed with the open interval from here to here.
Okay.
Sorry, what?
You set x equal to rx.
Thank you. X is in Rx, which is equal to this interval crossed with this interval, which is a subset of the ball.
Okay.
And we knew that the ball was a subset of U, so that gives us that R sub x is a subset of U.
Yeah.
So 8, then U is equal to the union for all little x in U of R sub x, which gives us that U is in tau. which gives us that the standard topology is a subset of tau. And then 9, blah, 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 blah. So tau is a subset of the standard topology. Therefore, tau is equal to the standard topology, which is what we were trying to prove. Any questions? You understand how the other direction would go, right? The other direction, the only problem is you've got some arbitrary open rectangle centered at a point, and now you need to find the open ball containing it that's also inside that rectangle.
So all the rectangles have a center point.
It doesn't even have to be a center point, really. Pick any point in there, I can still create an open ball around that point, right?
Yeah.
All I need is a minimum of the distance to here, 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 and here. Create a radius of that minimum distance, and you're done.
Yep, sense.
That's it. So, going the other way, it's almost identical. If you understand going the one way, I think you've pretty much got it. So, any questions about that proof? Anything you don't like? Anything you feel like we need to go over better? Alright. Now to the whiteboard. That's kind of blurry. Yeah, I might have to steal your spot. Have you move. How do I normally do this?
Usually
Jeez.
turn it.
But it's looking kind of blurry, isn't it? Oh well.
So, just to summarize, the topology of open balls and the topology of open rectangles are the same, pretty much.
Take the set of open balls as a basis. The topology it generates is the same topology that you can generate from a basis of open rectangles.
Okay.
The sets that they have in there aren't just open balls and open rectangles, they're all sorts of weird things. Right? We talked about the half plane, we talked about the set of everything except one point. There's lots of open things in there. Okay. So now we want to make some notes. Note a couple things and then we'll continue to our last proof. Okay, note 1. The standard topology on R to the n, which means R cross R cross R n times. You can think about this as like n-dimensional space. The standard topology on Rn is generated from the collection of open balls, beta, all the open balls centered at some point x in Rn, all the points within R of that point. Sorry, I said that bad. Just a set of, take any point in Rn, right? If we're thinking about three-dimensional, that could be this point right here. Here it is.
Okay.
Now take all the points within R of this point. That's going to give you a sphere, an open sphere. So in R3, this is an open sphere. In R2, it's an open ball. In R1, it's just an open interval. In general, we're just going to call them n-dimensional balls. So that's what we mean by the standard topology in general. And we proved it gives you a topology in R1, we proved it gives you a topology in R2, and that's all we proved, but now you're just going to take our word for it that R3, R4, R5, this also works. Good? And what do we mean by the open balls? So it's a set of all the open balls. What exactly is an open ball? It's all the points in Rn whose distance is less than R. What do we mean by the distance in 3 dimensions? We mean just the Euclidean distance. We proved this in 2 dimensions, but in 3 dimensions, 4 dimensions, it's the exact same thing. Proving it for 3 dimensions actually isn't that hard. You just use Pythagorean Theorem twice. So you can figure that out if you want to. Anyways, so that's just something to know. So from here on out, if we say standard topology on R3, you now know what I'm talking about. Another note, basis of open rectangles also generates a standard topology in Rn. So we proved that that's the case in R2. It's obviously the case in R1, right? Because an open rectangle in R1 is an open interval. An open ball in R1 is an open interval. They're the exact same thing. So,
Okay.
it's obvious in R1. We proved it for R2. Now we're noting that it's true in general. Okay? And then, last thing we're going to note is going to be a consequence of this theorem over here. But what we're going to note is that the fact that we use open balls or open rectangles is completely irrelevant. Pick any open shape you want. We could have used open hearts, I think is the one that he specifies. So we could have looked at all the open hearts, like that, and then made our basis all possible open hearts. That would have also generated the standard topology. And you do it in the exact same way as you do any other one. For any open heart, I can find and any point in there, I can make a ball around that point, and vice versa. For any ball, and for any point you pick in there, I can create a small enough open heart containing that point. The fact that you can make any shape, whatever you want, as small as you want. As long as it's a finite shape. Probably should have specified that. I don't know how you create an open shape that's not finite, but anyways. Okay, so what are we proving with theorem 1.13? Let tau be a topology on X, and let C be any subset of our topology. C is just some collection of open sets. Right?
Okay.
If for every open set in our topology, and for every point in that open set, there exists something in C such that X is in that thing in C, is a subset of U, then C is a basis for tau. I'm going to rewrite this now, but not the way the author has it. So this is the way the author has it. I'm going to change letters now on you to make it more obvious with what we've been using. Let tau be a topology on X, and let beta be a subset of tau. If for all U in tau, there exists X, and for all X in U, there exists B sub X in beta, such that X is in BX, is a subset of U, then beta is a basis on tau.
That makes sense.
That's what we're going to prove. Now, how does that give us this thing over here? So assume that we have this proved for a second. I want to finish the conversation here, and then we'll go on and prove it and be done. So assume that we know this for a second. What is this saying? This is saying pick any collection of open sets you want, as long as it satisfies this, as long as for every point in every open set, you can find one of those elements in your collection of open sets, such that this is true, then that collection of open sets you picked is a basis. So all the open hearts you can make we know are open sets in our topology, and as long as all our open hearts satisfy this property, then all our open hearts are a basis. And it's using the exact same thinking I was just saying before. How do we intuitively know it works? We know it works because for any open set we can think of in our standard topology, any open set you can think of in our standard topology, and for any crazy shape you want, so go get a kid's toys where they have all the different shapes that they shove through the hole, randomly pick one, and randomly pick a point in here. I can create that shape around this point, such that it's a subset of this whole thing. That's what it's given us.
So beta is a subset, right?
Beta is a subset of tau.
Okay.
It's a collection of open sets.
Okay.
So here's another way that we can think about this. Imagine that I just give you some random topology, and I say, now find a basis for this topology. How could you do that? Well, if you go and you pick some of the open sets, and you just make sure that the open sets you pick satisfy this property, then the open sets you picked are a basis. That's what we're proving.
Okay.
So you've got some random topology. I say pick a subset of the topology, pick out some of the open sets, and pick them out in such a way that this is true. Then I'm proving that what you just picked out is in fact a basis.
Okay.
Does that make sense?
Do we always know that there's a basis for a topology?
Yeah, there is always a basis for a topology because the topology itself can be viewed as basis for it. Because the topology has to include any union of its elements.
Oh, I see.
Alright, so let's prove this. So 1. Let beta be a subset of tau. Well, maybe I'll start with let tau be a topology on X. I guess that was already stated up there. Oh, well, I'll just write. Okay, let tau be a topology on X, and let beta be a subset of tau such that for all elements in tau, for all X in that element, there exists something in beta such that X is in that thing in beta is a subset of U. For those of you from logic, maybe writing it this way will be more helpful. Oops. Right? So, whichever of those is more helpful to you. Do you feel like you understand what it's saying? Okay. So, we need to prove that beta is a basis. We need to prove that it satisfies those two properties. We need to show that for any little x and big X, there's something in beta containing it. And then we need to show that anytime you have an intersection of two basis elements and there's a third basis element, that's a subset of their intersection containing the point, right?
Yep.
So let's do the first part. 2. Let X be any point in big X. Since big X is in tau, since big X is open, remember, a topology always contains the entire set. And what does this say over here? This says for any open set, for any point in the open set, there exists a basis element containing that point. That's a subset of the set. So since X is an open set, we don't really need let X in big X. We can just state it directly. It's going to fall easier than that. So maybe write, since big X is in tau, comma, then for all little x in big X, there exists b sub x in beta such that x is in b sub x. That's exactly what this says. This says for any open set, in our case we have the open set big X. For any point in the open set, there exists a basis element containing that point. Such that it's a subset of this, but all we needed was this part, right?
Yep.
So good with that part? So we proved the first part of its basis. Every little x in big X is in there, because big X is an open set. And we know for any open set, for any point in the open set, there exists a basis element containing that point. That was our given.
Right.
Okay. So now 3. Now we'll say, let B1, B2 in beta such that B1 intersect B2 is not equal to the empty set. So now we have two basis elements that intersect, right?
Okay.
I'm going to say equal to U is not equal to the empty set. Although, we don't really care, that's fine to the empty set. But, whatever their intersection is, we're just going to call it U so that we can reference it as U from here on out to help you see how we're using our given information. You with me so far?
Is that the same U you mentioned before?
Nope, new U.
Okay.
4. Since B1 is in tau and B2 is in tau, comma, then U is in tau. Right?
Yep.
Remember that beta is a subset of tau. So everything in beta is in tau.
Yeah.
So B1's in tau and B2's in tau. But the intersection of open sets is
Open.
Open.
open. So that's open, their intersection has to be open. Now what is our given information? What did we assume? We assume that for every open set, for every point in the open set, there exists a basis element containing that point that's a subset of it. Right?
Yeah.
Then, for all x in U, there exists bx in beta such that x is in bx is a subset of U, but U is just equal to B1 intersect B2. So for every point in the intersection, there exists a basis element containing that point, where the basis element is also a subset of the intersection.
Oh.
Which proves the second point.
Therefore, it's a basis. 6, therefore beta is a basis. Therefore, beta is a basis. And we're done.
Yep.
That's it. That's all we're trying to prove. And that's the end of our section on basis elements. And a basis for topology. Any questions? Any questions just in general with anything that we covered so far? Good. Alright, we'll be starting closed sets next time, instead of always talking about just open sets. Yeah, it's gonna get crazy.